let's take a look at groups of order 60. So for groups of order 60, we're going to take a look at this remarkable fact, which is either there's a unique Sylow 5 subgroup, or the group is simple. Okay, so to do this, we're going to use some facts about groups of smaller order, and in particular, I want to remind you of these two facts, which are that if you have a group of order 30, what we've showed is that either the 5 Sylow subgroup is normal or the 3 Sylow subgroup is normal. And if you have a group of order 12, then there's a characteristic subgroup of order either 2 or 4. So either you have the Sylow 2 subgroup, which is order 4 is normal, unique, or the intersection of the 3 distinct Sylow 2 subgroups ends up being a non-trivial and therefore characteristic non-trivial subgroup of order 2. All right, so let's take a look at groups of order 60. All right, so let's suppose you have a group of order 60 and the Sylow 5 subgroup isn't normal. What I want to show is that the group is simple, and we're going to argue by contradiction. So we're going to assume N is a non-trivial normal subgroup of G. And we're just going to think about what are the possible orders it could have. Well, you know, Lagrange says that the order divides the order of the group, and so the order of N can be something on the following list. 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30, right? Those are the possible non-trivial divisors of 60. And we would like to eliminate these. We'll eliminate these one by one. Well, of course, I can eliminate 5 because the hypothesis is that the Sylow 5 subgroup isn't normal. And now we are going to just go through the list and eliminate all the other possibilities. Okay, so let's first start with what if the order of N is 10? Well, if you have a normal subgroup of order 10, then inside that group itself, you can look at its 5 Sylow subgroups, and you know that this has to be congruent to 1 mod 5, and it has to divide the index of the 5 Sylow inside of 10, in 5 of N has to divide 2, and of course that tells you that the Sylow 5 subgroup is normal inside of there, so you have P, and it's therefore characteristic in fact. There's a characteristic subgroup of N, which is normal inside of G. P is a 5 Sylow subgroup, it has order 5, and so that tells you that P is normal inside of G, but of course P is a 5 Sylow subgroup in G as well, which is a contradiction, because that would have contradicted this 5 as a possibility. So that tells us that 10 doesn't work. Now, very similar arguments will work with 15 and 20, right? So if this is 15, or if this is 20, in either case, you also quickly find that the 5 Sylow subgroup of that thing is going to give you a normal subgroup in G, and it's a non-trivial 5 subgroup. And so those possibilities are also ruled out. So you can't have, what did I just do, 10 and 15. 15 and 20, sorry, 15 and 20. Okay. Let's move on down the list. Okay. So how about order 3? What if you have a subgroup of order 3? Well, if you have a subgroup of order 3, we're going to consider G mod N, which is a group of order 20. And as we just said, if you have a group of order 20, we were considering a moment ago subgroups of the group of order 20, those guys have normal Sylow 5 subgroups. So that means that there exists, let's call it, I don't know, some H bar, which is a normal subgroup of G mod N. The order of H bar is 5. That's a 5 Sylow subgroup. But now by the correspondence theorem, that gives us a normal subgroup of G, whose order is this times, what you're modding out by, which is 3. So order of H is 15. Okay? But actually, we just eliminated that as a possibility. We know that we can't have a subgroup of order 15. So that says that this 3 would have given us a 15, and so the 3 can't happen. Okay? Now, let's take a look at 30. Okay, if you have a subgroup of order 30, then what we know is that, as we recalled earlier, that a group of order 30, either has a normal subgroup of order 5, a Sylow and therefore characteristic subgroup of order 5, or a Sylow normal subgroup of order 3. But now, in either of those cases, that would give us that this Sylow subgroup would then be normal in the whole group. And so the group would therefore contain a normal subgroup either of order 3 or 5, but we know these can't happen. We've eliminated those already. So that says that 30 is up. All right, getting down the list. Which one is next? Let's do, let's do 6, right? So if the order of n is 6, it's then easy to check that the 3 Sylow subgroup of n is normal. And so then we get, again, our 3 Sylow subgroup of n, characteristic in n, and n is normal in G. So we get a normal subgroup of G of order 3. That can't happen, so then 6 can't happen. All right, we're doing well. Let's see. Let's do 2. Okay. Just getting through these numbers. Okay. If the order of n is 2, then now I'm going to consider G mod n, which is order 30. A group of order 30 has either a normal subgroup of order 3 or 5. So n3 of G mod n is 1, or n5 of G mod n is 1. Okay, now on the one hand, this would correspond to a normal subgroup of G mod n of order 3, which would then, by the correspondence theorem, give me a normal subgroup of G, where the order is 3 times, what am I modding up? By something of order 2, I would have gotten a 6. That can't happen. On the other hand, if it happened with, if the order of this normal subgroup in my quotient was 5, then I would have that the corresponding subgroup of G would be 5 times 2 is 10. And I know I don't have a subgroup of order 10 either. We'd eliminated that as a possibility. So because we'd eliminated 6 and 10, we can now eliminate 2. All right. That's 2. Okay. Just 2 more numbers to go. Let me do 4. All right, so now suppose that we have a normal subgroup of order 4. Again, I'm going to consider G mod n. The order of G mod n is 15. A group of order 15 has a normal Sylow subgroup of order 5. So we get some H bar, normal in G mod n. Order of H bar is 5. And then I get a subgroup of order 20, which is normal by the correspondence theorem in G. That can't happen, so we've eliminated 4. Because we had eliminated 20 before, we're only left with 12. But now if you have a normal subgroup of order 12, then what we know about groups of order 12 is they have characteristic subgroups either of order 2 or 4. Which would mean that you would have a normal subgroup of the whole group of order either 2 or 4. We'd eliminated those possibilities. So therefore, there's no normal subgroup of order 12 as well. Okay, so as long as you don't have a normal subgroup of order 5, you know, the Sylow subgroup isn't normal, then you can't have a normal subgroup of any other order in a group of order 60. Let's get a little reward for our toil. We can now notice that A5 is a simple group. Not hard to see now. Why is this a simple group? Well, inside of here, this is a group of order 60. So it's enough to show that I have more than one Sylow 5 subgroup. Well, I can look at the subgroup generated by this 5 cycle. It's a nice even permutation. Order 5 generates a subgroup of order 5. And I can look at the subgroup generated by 1, 3, 2, 4, 5. That guy. These are not the same cyclic subgroup. But they're both Sylow 5 subgroups. So I have more than one Sylow 5 subgroup, and that implies A5 is simple. Right? In 5 is not equal to 1. There we go.